Good morning, everybody. People are still starting to sign in here. I do want to remind you, and I have received emails from people already and talked to a couple of people about opening up that retake information for them. So, because we have somebody who hasn't taken the test yet, I have to do that individually. If you are qualified because you had all the homework in for sections 2.1 and 2.3, including the review, and you want to retake that 2.1 to 2.3 test, which was just on the two sections, I have to open that up for you individually. And you'll need to let me know either by sending me a short email saying, hey, I'd like to retake the 2.1 and 2.3 test, or hanging on at the end of the hour and letting me know that you'd like me to do that. But now we'll get going into today's. And as we went through 2.4, I'm sure that you noticed the enormous amount of detail in the problems that we're completing. And it's going to be the same thing today. I don't know that what we're going to do today will necessarily be difficult for you. In fact, I hope it's not. But it's very detailed work. And so we have to slow ourselves down a little bit and look at each and every step as we go through it. Because we are still going to be focusing on zeros, we're going to talk about complex zeros, which would mean we are including the imaginaries in this process, and the fundamental theorem of algebra, which you studied in Algebra 2. I will be able to use two major theorems, and here's the really big one, the fundamental theorem of algebra. You know, that's where all algebra came from. Carl Friedrich Gauss said, if it has a variable in it, and it has at least a first power to it, there are solutions, and mathematicians all over the world went nuts and said, let's find them all, let's figure out how you can do that. And then the linear factorization theorem, where we're breaking these down into linear factors. I really don't think we'll get ourselves to find complex conjugate zeros today and factor with real number coefficients. So this is another section that's going to take us 3 days to cover, but only has 2 assignments. And I'll talk about that when we get to the assignment piece here. But the big deal about all of this is we need the whole picture of what happens with any polynomial and its zeros. So it's important because these topics provide the complete story about zeros and factors of polynomials with real number coefficients. And especially if you are interested in becoming a software designer, anything with computers, the language of computers is math. And so what we try to do is create math equations that will show us the visual that we want on the computer screen. And of course, this gives you a much bigger picture than something you would just be able to do in Algebra 2. So, the two major theorems. These theorems are existence theorems. They tell us of the existence of zeros and linear factors, but they don't tell us how to find them. They're very broad. So the fundamental theorem of algebra, like I said, this one is extremely broad. A polynomial function of degree n has n complex zeros, real and non-real together. So some of those zeros may be repeat zeros. They may be repeated. And that deals with multiplicity, which, again, we'll kind of wait on because most of our day today is going to be spent on writing polynomial functions. But tomorrow's lesson, which you guys will be watching, that's right, Fridays we're supposed to go back to just digital lessons. So that'll be a recorded lesson talking about those zeros and the multiplicity piece. And then linear factorization theorem says if f of x is a polynomial function of degree n greater than 0, then f of x has precisely n linear factors, which makes sense because we know that there are n zeros in it. And so we break it down into x to the first, x to the first, x to the first here, those being linear. So where a is the leading coefficient of f of x, and all of these z's, z sub 1, z sub 2, all the way to z sub n, are the complex zeros of f of x. The z sub I are not necessarily distinct numbers. Remember that some of them may be repeated, and that has to do with the power that they will be raised to, the exponent for that linear factor. Basically, if you have a polynomial of degree n, you will have exactly n factors or zeros. And it does include both real and non-real. So remember, we are working with imaginary. We're not just going to stop and say, hey, no more real solutions. We're going to find them all. And a big part of computer programming would be figuring out how to manipulate our polynomials so that they cross the x-axis when we want them to cross, and they don't when we don't want them to cross. And that has to do with having some non-real zeros as you work through this, because the non-real zeros, of course, don't ever cross the x-axis. Fundamental polynomial connections in the complex case. The following statements about a polynomial function f are equivalent if k is a complex number. X equals k. Well, that's where we have found all of our solutions. So solutions or roots of the equation f of x equals 0. And that we've known all along, whether or not it was real or imaginary. K is a 0 of the function f. Now, being a 0 doesn't mean that it's necessarily going to actually cross the x-axis. It just means that it's a 0. Crossing the x-axis makes it an x-intercept. X minus k is a factor of f of x. So you'll notice here that this has been shortened from the previous box that we had about these zeros. The connection that's lost with those non-real zeros is they don't appear as x-intercepts of the graph. So that would be, hey, I need this to be a 7th degree polynomial so that it'll show up the way I want it to on the computer screen, but I only want it to cross the x-axis 3 times. Well, then you're going to need to have 4 imaginary zeros so that it doesn't actually cross at those other 4 spots. So we are going to do a lot of this today, creating a polynomial from its factors. And we're exploring fundamental polynomial connections. It says write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. Well, that's kind of backwards because this is already broken up into its linear factors. So yesterday we talked about how there really are 2 ways to write those zeros, and one of them would be writing it as ordered pairs. But in this case, especially because we're starting to talk about imaginaries, and imaginaries aren't going to necessarily give us ordered pairs for our zeros, this is where that notation of f of, and in this case it would be 2i and negative 2i, that explains it much better, what's going on. It's saying, hey, these are zeros, but it's not an ordered pair because these would not be ordered pairs on our graph. So there's the identifying the zeros of this function. And the x-intercepts of the graph, well, because these are imaginary, it's not going to cross. We don't have a real 0 there. So this won't have any. It'll have no x-intercepts. And of course you could do that after you've written the polynomial as well, but it's easy to see it in the factored form. So now, standard form means no parentheses, have it all multiplied out, have it in order from highest power all the way down. So with this one we just use FOIL. We have 2 binomials, first times first, x squared. Outside times outside is positive 2ix, and inside times inside is negative 2ix, which is great because that would not be fun to work with. And it's gone. They cancel each other out. And then we have minus 4i squared. And we remember, oh, wait a second, I squared is negative 1. And then, if we take negative 1 times negative 4, we get positive 4. Now, this is the notes, for distance learners and everybody that's not here. This one, this middle step, I kind of consider that, a baby step. But I want everybody to be able to see that, hey, that I squared is a negative 1. Most of you will probably be able to just go from this top step to this bottom step. But if you realize while you're going through the homework that you're constantly losing the negative because you're doing that, then go ahead and put that baby step in the middle there. Don't lose track of those negatives. That is the most common mistake made in mathematics. So now let's see if we've done everything we were supposed to do. Write the polynomial function in standard form. Done. There it is. Identify the zeros of the function and the x-intercepts of the graph. There's the zeros, no x-intercepts. Now, small points would be taken away. Some of you have not been leaving that label of f of x all the way through as you work with this. Make sure that when you're working on a test that you're paying attention to those details and you're bringing that f of x down with you to show this is actually the exact same graph. You know, if we put this into the calculator as the original equation or the one that we just developed that's in standard form, we should see exactly the same thing. If we don't, we did something wrong. So carry that information with you. Be detailed. B, we can start to see, getting a little tougher. This one has 3 linear factors. So might as well start off with the zeros. And remember, each of these came from x minus a, so you could think of it that way, or you can just think, well, 5 minus 5 would be 0, so 5 is my 0. And then we'd have square root of 2i and negative square root of 2i. So there are the zeros. Now, with this one, we recognize, well, this is a real one, and that would actually cross. So that's an x-intercept at 5, 0. So notice the distinction between the two. The f of notation that we're using is to say, hey, this is a 0. But graphically, we're only going to use the real zeros to show which ones are actually crossing. All right, now, this is where every once in a while somebody says, well, I'm going to save the 2 hard ones for last. Oh, if you do that, you're actually making a huge mistake, because what we want to do here is get rid of those imaginaries as soon as possible. And we see a sum and difference pattern right here. So that means good things are going to happen if we multiply those two together. So this needs to be your starting place. Don't stay away from it just because it has imaginaries in it. Go after what appears to be the most difficult part first. So first times first is x squared. Outside times outside and inside times inside, we're not even going to bother talking through because we know this is a sum and difference pattern and they're going to cancel out. Last times last would give us a negative. Square root of 2 times the square root of 2 is the square root of 4. And then I times I is I squared. Again, I'm writing down some steps here that after we do a couple of these, I'm probably going to skip. Because you know what the square root of 4 is. It's 2. And you know what I squared is. You know it's negative 1. So you might very well skip this step right here that I just completed. So we really need to take the quantity x minus 5 times the quantity x squared plus 2. And we'll do FOIL, or we might do FIOL in this case, so that we don't have to reorder these in the end. X times x squared is x to the 3rd, and then if we do the inside times the inside, we'll get the x squared term. And then outside times outside will give us the x term. And then last times last for the constant. And again, keeping that label of f of x because this is just an equivalent polynomial expression. The linear factors, if we graph that in the graphing calculator, should look exactly the same as our standard form that we have here. So that's another thing that if you have time to check, before you move on to the next question, because on our tests you have to finish one question before you move on. You look down at the clock, you see you have plenty of time. Maybe pop both of these into your graphing calculator. You should only see one graph because if you've done it right, they're exactly the same. Now we notice they gave us another factor. So we've gone from something squared to a cubic, and now we have a quartic. And we need to list those zeros. And we can see here that we're going to have 3, and that one would be there twice. And that's because if we were to truly write this the way it should be, which is the quantity x minus 3 squared, it would have a power of 2. So as we get more into that tomorrow, we're going to talk about this multiplicity of 2 piece. And what that tells us is if it's a real 0, it actually, the graph is going to be tangent to the x-axis at that point. It's going to hit it and it's going to bounce off, so it gets to count twice. And that's why this is still going to be a quartic when we get done. Then I have my I and negative I. And I'm going to start writing that with a little plus or minus piece here. So the realization is, well, it only has the one x-intercept up there because it only has one real x-intercept. So the x-intercept is going to be 3, 0. And it is a multiplicity of 2. Now, we have to figure out what should we do. And again, go after the imaginaries right away. You don't want to be distributing an I through a bunch of parentheses. That's no fun. And I probably would go ahead while I'm at it and multiply those two binomials together in the front, the x minus 3 and the x minus 3. Again, showing more than is necessary. I'm sure for that second one, lots of you immediately went to x squared plus 1. Now, we have all kinds of choices while we're doing these. We could take x squared times everything in the second set of parentheses, negative 6 times everything in the second set of parentheses, 9 times everything in the second set of parentheses. Myself, I prefer having the shorter, the binomial, in the front. Less distributing. So less times that you can make mistakes. Now you might say, well, it ends up exactly the same amount, but visually it feels like it's less because now we distribute an x squared through the second set of parentheses and then a 1 through the second set of parentheses. So we'll do that. And then with this one, we see some like terms. Not a ton of them, just our x squareds in the middle there. And we end up with x to the fourth minus 6x to the third plus 10x squared minus 6x plus 9. That was 4 linear factors. We know what's going to happen. 2, 3, 4, 5 of them. So this one, again, a little more complicated because now we have 5. I know it says you try, but what I want to do is talk to you about this x minus 2 that's here really for a multiplicity of 3. So I'd rather we kind of work through this one together. And the first things first, let's talk about those zeros. F of positive and negative 3i will give us 0, and then f of 2 will give us 0. And then our x-intercepts are only the real pieces of this. So the real piece of this would be the 2, so that's going to be 2, 0. And that has a multiplicity of 3. Now, because it has a multiplicity of 3, that means it actually crosses the x-axis. Anytime we have an odd multiplicity, it crosses the x-axis. Anytime it's even, we have that tangent, that bouncing off piece going on. Now, the reason I want to talk to you about this one is I'm pretty sure there was something that they cut in the spring that you didn't see. And that something involves Pascal's triangle. So just to make sure, because I think they had to cut this given that we had all the COVID stuff in the spring last year. Is there anybody here that remembers talking about Pascal's triangle last year? Would have been in the spring. Okay, so it was something that they cut, which means we will have to multiply two of these together using FOIL and then distribute the other one because you didn't learn about Pascal's triangle. Pascal's triangle is it's a really cool feature. Blaise Pascal actually created a computer language hundreds of years before computers were ever even thought of. And what he did was he made a triangle where he said, I'm going to start with ones. And then what I'm going to do is I'm going to add the numbers above, start and end with ones, and add the two numbers above. So he started with those 3 ones, and then he said, okay, starting with a 1, 1 plus 1 is 2, ending with a 1. 1, 3, 3, 1. And he kept going, creating Pascal's triangle. And later, it was found out that this has all kinds of applications in probability. It has, for what we're doing right here, binomial. It's the binomial theorem of how you can multiply when you have cubics or things raised to the 4th power, 5th power, and beyond. So it's really interesting. I don't know that we'll get to talk about that then since you guys didn't get it last year, but we'll see. So we're going to have to go after this one a little bit differently. We want to multiply those two together first. So that will give us, obviously, x squared. It's got the sum and difference going on, so minus 9 I squared. And then we probably want to start by just multiplying two binomials together first and getting x squared minus 4x plus 4. So in the front, I'll have x squared plus 9. And now I need to figure out what I have when I take x minus 2 times the quantity x squared minus 4x plus 4. And that'll be x to the third minus 4x squared plus 4x. Probably didn't leave myself enough room here. And then minus 2x squared plus 8x minus 8. Running into my 0 over there. So let's go ahead and combine some like terms. So that's not so enormous. We have x to the third minus 4x squared minus 2x squared, so minus 6x squared plus 12x minus 8. I'm kind of squishing here, so if you see an error, please say something and stop me before we keep going. Then we'll go ahead and distribute the x squared, and then we'll go back and distribute the 9. So go ahead and do that. I'm going to stop there to see if everybody can double check me. X to the fifth minus 6x to the fourth plus 12x to the third minus 8x squared plus 9x cubed minus 54x squared plus 108x minus 72. And running out of space actually gave me an opportunity to show you another way that some mathematicians will do these, and it has to do with lining up vertically everything that has the same power. And sometimes that helps you keep track of them a little bit better. This was my only x to the fifth, my only x to the fourth, but I did have 2x to the third terms, a couple of x squareds, and again, it just keeps it organized. Because like I said, this is probably not the toughest stuff we've ever done, but it's really involved. There's a lot of steps. So we'll have x to the fifth minus 6x to the fourth plus 21x cubed minus 62x squared Oh, I'll write it down here. Plus 108x minus 72. I keep wanting to move the screen up, but then I remember you guys have that big blind spot right here. So we have our f of x as x to the fifth minus 6x to the fourth plus 21x cubed minus 62x squared plus 108x minus 72. Phew. It bothers me that we couldn't talk about that Pascal's triangle, but I think we get another opportunity to speak to that later. So that'll definitely be something, whether or not you decide to take AP statistics or calculus, you'll probably revisit Pascal's triangle again. All right, that was 5 of them. Notice it kind of switches. It does, but it doesn't. We're going to have, from time to time, fewer of those zeros, but they might become a little bit more complicated. So we've got complex conjugate zeros to talk about. And remember, the complex conjugates are a plus bi and a minus bi, which tells us we've already been using complex conjugates today, because when we multiplied that sum and difference formula, we were really working with those complex conjugates. So suppose that f of x is a polynomial function that has real coefficients. If a and b are real numbers with b not equal to 0, a plus bi is a 0 of f of x, then its conjugate, a minus bi, is also a 0 of f of x. Yesterday we talked about how if we had an irrational 0 like the square root of 5, then negative square root of 5 also had to be there because they come in pairs. Well, it's the same thing for the imaginary zeros. You never get just one. And you can kind of think through how our completing the square process works and the quadratic formula and realize, oh yeah, there's going to be a plus and minus in both of those situations. So they will both occur. That means, in a nutshell, all non-zeros, all non-real zeros occur in conjugate pairs. So from time to time, they're only going to give us one, and we have to stop and say, wait a second, that doesn't just come alone. It also has its conjugate. So creating a polynomial from its zeros, find a polynomial function with integer coefficients with minimal degree if negative 5, 3, and 6i are the zeros. And the first thing we should do is say, oh, they're trying to pull a fast one. Because if 6i is a 0, so is negative 6i, because they always come in pairs. Now, the rest of this should just happen naturally. If we figure out that 6i and negative 6i would both be zeros, 1, 2, 3, 4, this should be an x to the fourth, a quartic, a degree 4 polynomial, and it should just happen that way naturally without us doing anything else. Now, they did call it a polynomial function, so we can't just put down y, we have to put f of x down. And then we would have, remembering that these always came from an x minus a, so we'd have x plus 5, x minus 3, x minus 6i, and x plus 6i. And now, that one should look and feel like, hey, we did that just a little while ago. So, here's what I want you to do. I'm not going to talk through this one, but I'm going to go ahead and write it out while you are giving it a try, and then let's see if we can all end up at the same place. Once you have it, stop and take a peek. If it doesn't match, try to go back up and find where your mistake is. Best practice with this is just to take your time the first time through. Try not to speed through it too much. I hope I gave you enough time. If I did, just blink me and unmute. So unmute yourself and then mute yourself back, and I'll see that you had it right. Just a quick unmute and mute. Okay, either I didn't give you enough time or many of you did not get this right. All right, I heard a few more unmutes. Does anybody still need more time? Unmute and let me know. All right, so like I said, we're not necessarily saying just keep giving more zeros to make these difficult. What we're doing is we're increasing the difficulty level of the zeros themselves. And that starts happening in this example. So this one says finding a polynomial from the given zeros, and you're like, well, we just did that. Big deal. Write a polynomial function of minimum degree in standard form with real coefficients whose zeros include 3, -3, 4, 2 minus I. Now hopefully right away you thought, oh, they're not going to get me. Those imaginaries come in pairs. So if 2 minus I is there, 2 plus I is also there. So far we look at this and just say, okay, it's a quartic. Big deal, we did one of those. Polynomial function. We get started thinking about our x minus a. So this would be x plus 3, x minus 4, and then we get to those two. And we realize this has taken us to a new level, because this will be x minus, and I'm going to need a second set of parentheses, 2 minus I. And then another set will say x minus the quantity 2 plus I. Now I hope your first instinct is, well, we're going to have to distribute that negative, because we can't have parentheses inside parentheses. That's always the first thing we have to do. So I'm going to leave these front two alone for a second and go after my last two linear factors, distributing the negative. And trying to figure out, what could I do to make that easier to multiply? I mean, seriously, am I going to take x times everything back here, -2 times everything back there, I times everything back? That's not what we did with the other ones. With the other ones, we had a nice sum and difference pattern, and that made things go faster. Well, that's what we need to do here. We need to relocate our parentheses so that they'll show us a sum and difference pattern. So look at these two. They both have the x minus 2. But this is a plus, and this is a minus. So if I relocate my parentheses, now it's a sum and difference pattern. That I can do. So I'm going to go ahead and multiply my first two real zero binomials here. So we have x squared minus 1x minus 12. And then in the back, I'm going to start to use a bracket here to distinguish that from our parentheses. I'm going to have to take first times first, which would be x minus 2 squared. And then last times last would be minus I squared. So now I have a little bit of work that I have to do inside those brackets. And sometimes people will write it out as x minus 2 times x minus 2 right there and do FOIL. Sometimes people will come down here and use a little blank space to figure out what x minus 2 times x minus 2 is. I don't care, as long as I can see how you got it. I mean, that's what has to happen. I have to see your steps. So I would say most often people just put it right in the brackets. So we had that minus I squared that becomes a plus 1 in the back. But we can't do anything with that until we've figured out what x minus 2 times x minus 2 is. And now we can put the 4 and the 1 together. Whew. We're not done yet, but the most important part of this we completed way back up here, where we distributed that negative and then we remade that pattern, that sum and difference pattern, to make this a little bit easier to work with. So now, this is what I'm going to tell you. Just go slow. Take the first x squared times everything in the second set. Take negative x times everything in the second set. Take negative 12 times everything in the second set. And try to keep them organized so you don't lose anything. That's if somebody makes a mistake on these on the test, it's usually a negative or they lose something. If you take a peek at mine, you see that I'm using that vertical technique. X to the fourths, x to the thirds, x squareds, x's constant. You don't have to do that. If you're able to put them all horizontally and you don't lose anything as you are adding them together to combine like terms, then you're okay. Scroll that down so it's not in a blind spot. Trying to give you some time here to finish that up. And then check to see f of x equals x to the fourth minus 5x cubed minus 3x squared plus 43x minus 60. And when we're working with long problems like this, I really hope that if you guys are falling behind because I'm going too fast, because nobody uses their camera anymore. Everybody uses icons. So if you need more time, you need to speak up. You got to unmute and say, Cedarholm, can you give us another minute? Anybody need more time on this one? All right. Well, then we need to keep going. So here's another one that's a little more complicated. Doesn't look like it, only has 3 zeros up there. So finding a polynomial from given zeros, write a polynomial function of minimum degree in standard form with real coefficients whose zeros include 1 plus 2i means 1 minus 2i is also there. And 1 minus I means 1 plus I is also there. So this problem is going to have two different sets of more developed zeros, more developed complex zeros. So our x minus 1, that's the only one that's not going to take a lot of work in here. And then we have to be very careful and put our x minus, I guess I don't need the brackets yet, x minus the quantity 1 plus 2i, and x minus the quantity 1 minus 2i. And then we're going to need x minus the quantity 1 minus I, and x minus the quantity 1 plus I. And just like last time, get rid of the parentheses first by distributing the negative. So far, so good? Now go back and put in the parentheses that will make these sum and difference patterns. They both have the x minus 1. One will now have minus 2i and the other plus 2i. Those will both have x minus 1, but they'll have a plus I and a minus I. So now the second and third set of parentheses are going to be x minus 1 squared minus 4i squared, and then x minus 1 squared minus I squared. And now, like I said, with this one, because you have x minus 1 squared in both spots, you might want to just show me some work off to the side and just substitute in. Substitute that x squared minus 2x plus 1 in there. And then you can change your I squareds to a negative 1. So negative 4 times negative 1 will be positive 4. And then minus an I squared will be minus a negative 1, which is a plus 1. And then we need to combine like terms. Phew. And we see there's still a lot of work ahead of us. But this is a great spot here to stop and say, okay, everything looking good. Did I get all the I's out of everything? And then I will usually hold off on that x minus 1 and multiply these two trinomials together first. Once you have it all multiplied out, combine your like terms. Take a second to double check. And then distribute the x through the second set of parentheses, distribute the -1 through the second set of parentheses, and then we'll combine like terms. I'm going to have to give myself some more space here. All right, I just looked at the clock. Get so into this that it's hard to remember, hey, we only have the 15-minute class period right now. So, we only have about 3 minutes. This will have to be our last one. Obviously, more and more you see why pre-calculus tests may just have 6, 7, 8 problems on them. I mean, like I said, this isn't the toughest thing we've ever done. It's just there are a lot of steps, and you have to work very carefully and slowly through all of those. So that is where we're going to have to end today. Now, that, of course, means when I give you the homework here, we won't be able to do everything that's on there, but you probably knew that was coming anyway because we have 3 days to cover this material and we only have 2 assignments. And you will need to probably stop after 1 to 15 odd, unless you're feeling like, I remember this stuff from last year, but I guess I would ask that you stop after 1 to 15 odd, because we need to review multiplicity again, and that's what we're going to be doing tomorrow, is talking a lot about that. So most of our time today was spent on an objective of writing these polynomial functions. So it looks like, hey, that's not a long assignment, but remember the involved problems that we're working on. So 1 through 15 odd.